Hi everyone, this is Dr. Hopkins presenting your second video on the properties of lanthanides. And in this video I'm going to describe a little bit about the electronic structure within the 4f electron configuration of the lanthanides. Alright, so as we said in the last video, the most lanthanides occupy or have a 3 plus electronic configuration, which is xenon with 4f and however many 4f electrons, so the valence electrons on the 4f electrons. And we can describe the energy levels within these 4f electrons based on term symbols, or Russell-Saunders coupling of angular momentum. And so the term symbols have the 2s plus 1, that's our multiplicity, tells us how many spins, whether singlet, triplet, doublet, etc. L tells us our total orbital angular momenta, so what are our electrons in terms of m sub l's, and add those up. And then J is the sum, where we're just adding these two angular momenta together, the spin and the orbital. And so we can get J's that run from L plus S all the way down to L minus S. And you can see in the table where the labels L, if you have 0 orbital angular momentum, we give it a capital S, P, and D, and so forth, and we keep going up. All right, and then at the end, you end up with 2J plus 1 M sub J at total angular momentum states, okay, which will be important. All right, so if we're going to describe based on those term symbols, what are the lowest energies? So if we want to know what's the ground state and what are the next highest term symbols as we go up, the ones with the highest spin multiplicity have the lowest energy. And then next we would go down, if we have the same spin multiplicity, well then the highest orbital angular momentum have the lowest energy. And then if the F shell, so if we're looking at the J's, if the F shell is less than half filled, and actually this can apply for P and D shells as well. So they're less than half filled, so if we have less than 7, the lowest J will have the lowest energy. If it's half filled or more, the highest J has the lowest energy. So let's look at an example down here at the bottom where we have neodymium. It is a xenon core, which I've omitted, and we have 4f3, so we have 3 electrons. Now we have the boxes with all of the m sub l's. So our S, let's do our spin multiplicity first. So the largest spin multiplicity would be all spin up or all spin down, because this would just be an absolute value. So if they're all spin up with 3 times the 1/2 m sub s, this gives you 3 halves. And so that's represented here. And so that would be our highest S. And then if we were looking at what's the highest L, well then we would put the 3 spin electrons into the highest m sub l. So we put 3 plus 2 plus 1, that's an m sub l that's a total of 6. So an L max of 6. So if we added these electrons to any of these others we added here, it would subtract and so forth. So we would we have a lower total orbital angular momentum. So our L max is 6, our S max is 6. So our J can be from L plus S, so 12 halves plus 3 halves is 15 halves, down to L minus S, which is 12 halves minus 3 halves, which is 9 halves. And so in this case, we are less than half filled. So it's a quartet, okay, because it has 3 halves, 2s plus 1, so 2 times 3 halves plus 1 is 4. It has an L of 6, which is I, has the letter I. And then the lowest J has the lowest energy, so it would be the J equals 9 halves. So the quartet I 9 halves would be the lowest term symbol for this. And so if we're looking at all of the ground states, so we follow Hund's rules and we put our electrons together, and you can see something like europium, which has 6 electrons. It has a spin multiplicity of 7. That's all of them spin up in all of those various states. But then you can see that the J is equal to 0. And so forth. So we're looking at our ground state configurations of all of the 3 plus ions. So europium 7f0, terbium, which is half or higher, is 7f6. So you can see there's some symmetry, there's some pairing with respect to these the number of electrons. So we have up to 6 electrons, and then these have the same 2s plus 1 L, but opposite, different J's in terms of the ground state. All right. And so based on this, so we're looking at this, the electronic structure. We've constructed a Hamiltonian that describes those 4f electrons, and we have the effective electronic Hamiltonian, including all of the electronic terms, electron-electron repulsion, which kind of arises, that gives us our 2s plus 1 and L, right? So that gives us our spins, and that gives us our orbital angular momentum, and those are represented as the 2s plus 1 L. And then when we couple them, we put spin-orbit coupling together, then you end up with the J, right? So then we have the 0, 1, and 2. We have the splitting. And then there's a further splitting. So if we just have the lanthanide 3 plus ion in gas phase, no structure, all of these will split, but all of the m sub j's within each of the j equals 0, j equals 1, j equals 2 in this case, will be degenerate. But if we put it in a structure, we allow it to bond with something, you end up with the crystal field Hamiltonian or the ligand field Hamiltonian, which then splits those m sub j levels, and it actually splits them. They end up with degeneracy based on symmetry and so forth. So the structure leads to, so the structure that the lanthanide ion is in leads to subtle differences in the energies, but in general, the 5d0, the 5d1, and 5d2, those are located based on fundamental, the effective Hamiltonian of the 4f electrons of the lanthanide, not the interaction with the ligands, because remember, they don't participate in covalent bonding. And this is the opposite. So I show the kind of the importance of these terms in terms of the Hamiltonian. And this crystal field Hamiltonian is much smaller, so we get subtle changes, but we always have similar energies. That's not the case with transition metals and so forth, where the crystal field Hamiltonian is much, much more important. Okay, so what this means is within any 4Fn configuration, we have a large number of 4F electrons. We're going to have a large number of 2s plus 1 and L states. We're going to have a large number of Russell-Saunders term symbols. You know, in terms of the 4F6 and 4F8, the europium and terbium, the most common visible emitting lanthanides that we use, you get 295 and you get 3003 m sub j levels. So you have a large number of possible energy levels within these. So they're very dense. And this diagram, this graph or figure here is kind of the classic. It's general to all of the across the lanthanide series, the 3 plus, and gives you an idea of all of these states. And these are the all of the term symbols, and not even split out in terms of their m sub j. So you can see the large density of excited states that you can get. And here we have an arrow pointing to the emitting states of the 5d0 of the europium 3 plus. The ground state is the 7f0, and so you can see it goes all the way up to 7f6. And with the terbium, the emitting state is a 5d4. I don't have an arrow to it, but it's just over here to the right. And then you have the opposite where your ground state is 7f6. So this shows all of those term symbols, gives a general energy location, and for the most part, those energy level locations don't change. So this is in the fluorides. They don't change very much depending on what ligands you put on them. They change slightly, but what the bigger change is the splitting within each of those term symbols. So in the next video, we will describe spectroscopy.